In astronomy, Kepler's laws of planetary motion are three scientific laws describing the motion of planets around the Sun. Kepler's laws are now traditionally enumerated in this way. Figure 1. Illustration of Kepler's three laws, with two planetary orbits. 1. The orbits are ellipses, with focal points 1 and 2 for the first planet, and 1 and 3 for the second planet. The Sun is placed in focal point 1. 2. The two shaded sectors A1 and A2 have the same surface area, and the time for planet 1 to cover segment A1 is equal to the time to cover segment A2. 3. The total orbit times for planet 1 and planet 2 have a ratio of 13/2 or 23/2. Astrodynamics orbital mechanics equations. Kepler's laws. 1. The orbit of a planet is an ellipse with the Sun at one of the two foci. 2. A line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. 3. The square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. Most planetary orbits are almost circles, so it is not apparent that they are actually ellipses. Calculations of the orbit of the planet Mars first indicated to Kepler its elliptical shape, and he inferred that other heavenly bodies, including those farther away from the Sun, have elliptical orbits also. Kepler's work broadly followed the heliocentric theory of Nicolaus Copernicus by asserting that the Earth orbited the Sun. It innovated in explaining how the planet's speeds varied and using elliptical orbits rather than circular orbits with epicycles. Isaac Newton showed in 1687 that relationships, like Kepler's, would apply in the solar system to a good approximation as consequences of his own laws of motion and law of universal gravitation. Together with Newton's theories, Kepler's laws became part of the foundation of modern astronomy and physics. Nomenclature. It took nearly 2 centuries for the current formulation of Kepler's work to take on its settled form. Voltaire's Elements de la Philosophie de Newton, Elements of Newton's Philosophy, of 1738 was the first publication to use the terminology of laws. The Biographical Encyclopedia of Astronomers, in its article on Kepler, page 620, states that the terminology of scientific laws for these discoveries was current at least from the time of Joseph de Lalande. It was the exposition of Robert Small, in an account of the astronomical discoveries of Kepler, 1804, that made up the set of 3 laws, by adding in the third. Small also claimed, against the history, that these were empirical laws, based on inductive reasoning. Further, the current usage of Kepler's second law is something of a misnomer. Kepler had 2 versions of it, related in a qualitative sense, the distance law and the area law. The area law is what became the second law in the set of 3, but Kepler did himself not privilege it in that way. History. Johannes Kepler published his first 2 laws about planetary motion in 1609, having found them by analyzing the astronomical observations of Tycho Brahe. Kepler's third law was published in 1619. Kepler in 1621 and Godefroy Wendelin in 1643 noted that Kepler's third law applies to the 4 brightest moons of Jupiter and B1. The second law, area law form, was contested by Nicholas Mercator in a book from 1664, but by 1670 he was publishing in its favor in Philosophical Transactions, and, as the century proceeded, it became more widely accepted. The reception in Germany changed noticeably between 1688, the year in which Newton's Principia was published, and was taken to be basically Copernican, and 1690, by which time work of Gottfried Leibniz on Kepler had been published. Newton is credited with understanding that the second law is not special to the inverse square law of gravitation, being a consequence just of the radial nature of that law, while the other laws do depend on the inverse square form of the attraction. Carl Runge and Wilhelm Lenz much later identified a symmetry principle in the phase space of planetary motion, the orthogonal group O, for acting which accounts for the first and third laws in the case of Newtonian gravitation, as conservation of angular momentum does by rotational symmetry, for the second law. First law. The orbit of every planet is an ellipse with the Sun at one of the two foci. Figure 2, Kepler's first law placing the Sun at the focus of an elliptical orbit. Figure 4, heliocentric coordinate system, R, for ellipse. Also shown are semi-major axis A, semi-minor axis B and semi-latus rectum P, center of ellipse, and its two foci marked by large dots. 4 equals 0, R equals RMIN, and 4 equals 180, R, RMAX. Mathematically, an ellipse can be represented by the formula where R are polar coordinates, D is the focal parameter, and is the eccentricity of the ellipse. Note that 0, 1, for an ellipse, in the limiting case equals 0, the orbit is a circle with the Sun at the center, see section 0 eccentricity, below. For a planet, r is the distance from the Sun to the planet, and is the angle to the planet's current position from its closest approach, as seen from the Sun. Examples: semi-major axis orbital eccentricity, interfocal distance location of F to Jupiter 7,783 m in kilometers, 0.04838675 m in kilometers, roughly halfway between Mercury's 58 m in km and Venus's 108 m in kilometers, orbital distances. Saturn 14,267 m in kilometers, 0.05386 to 154 m in kilometers, roughly at Earth orbit distance, 150 m in km. Second law. A line joining a planet and the Sun sweeps out equal areas during equal intervals of time. The same blue area is swept out in a given time. The green arrow is velocity. The purple arrow directed towards the Sun is the acceleration. The other two purple arrows are acceleration components parallel and perpendicular to the velocity. This law relates radial distance and angular velocity in elliptical orbits. That is, in a perfectly circular orbit, the orbital radius of the satellite would be constant, and therefore so would be its observed angular velocity. In elliptical orbits, the orbital radius of the satellite will vary, and therefore so will its angular velocity. This is shown in the above animation, where the satellite travels faster or greater angular velocity when closer to the parent object, than slower less angular velocity at a more distant radius. The result is that the blue sectors are shorter but wider when close to the body, than longer but narrower at a greater distance. Kepler's second law states that for a given elliptical orbit, any two sectors of equal time duration will have the same area. This implies that radial distance and angular velocity have an inversely proportional relationship. In a given orbit, angular velocity is minimum at apoapsis and maximum at periapsis. The constant of proportionality is the rate at which area in the ellipse is covered. Examples: perihelion distance, perihelion speed, aphelion distance, aphelion speed, sector area swept in 1 second, Mercury 46.0 m in kilometers, 59,000 m/s, 69.8 m in kilometers, 38,900 m/s, 1.3565 1015 m2 for both perihelion and aphelion, Sednon 11,423 b in kilometers, 4,640 m/s, tilde 140,000 b in kilometers, tilde 430 m/s, 3.01 1016 m2, based on perihelion measurements, 2.65 1016 m2, based on aphelion measurements. Note: the point speeds are worked out based on B equals gm, 2/d1/a. The area swept figure is less accurate for Sedna due to the imprecise degree to which its orbital parameters are currently known. Third law. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. The third law, published by Kepler in 1619, captures the relationship between the distance of planets from the Sun and their orbital periods. Kepler enunciated this third law in a laborious attempt to determine what he viewed as the music of the spheres according to precise laws, and express it in terms of musical notation. So it used to be known as the harmonic law. Mathematically, the law says that the expression has the same value for all the planets in the solar system. Examples: period and semi-major axis, in relation to Earth, period 2, semi-major axis 3, in relation to Earth, period, and semi-major axis, in real terms, period 2, semi-major axis 3, in real terms, ratio Venus 0.615 years, 0.7230, 0.3785, 0.3785, 19.4 mn seconds, 1.082 1011 m, 3.769 1014. 1.267 1033 13.36 to 1018 Neptune 164.8 years, 30.10 27,160 27,280, 5.2 bn seconds, 4.498 1012 m, 2.704 1019. 9.103 1037 13.366 1018. Formulary. The mathematical model of the kinematics of a planet subject to the laws allows a large range of further calculations. First law and the geometry of the ellipse. At equals 0, perihelion, the distance is minimum. At equals 90, and at equals 270, the distance is equal to the semi-latus rectum. At equals 180, aphelion, the distance is maximum. The semi-major axis is the arithmetic mean between RMIN and RMAX. The semi-minor axis B is the geometric mean between RMIN and RMAX. The semi-latus rectum P is the harmonic mean between RMIN and RMAX. The eccentricity is the coefficient of variation between RMIN and RMAX. The area of the ellipses. The special case of a circle is equals 0, resulting in R equals P equals RMIN equals RMAX equals B and A equals R2. Second law, mathematical derivation. In a small time the planet sweeps out a small triangle, or, more precisely, a sector, having baseline and height and area, and so the constant real velocity as the planet moves faster when it is closer to the Sun. The area enclosed by the elliptical orbit is so the period satisfies, and the mean motion of the planet around the Sun satisfies. Third law, modern formulation. The modern formulation, with a constant evaluated, reads as where T is the orbital period of the orbiting body, m is the mass of the star, g is the universal gravitational constant, and r is the radius, i.e. the semi-major axis of the ellipse, in the full formulation under Newton's laws of motion, and should be replaced by where m is the mass of the orbiting body. Consequently, the proportionality constant is not truly the same for each planet. Nevertheless, given that m is so small relative to m4 planets in our solar system, the approximation is good in the original setting. 0 eccentricity. Kepler's laws refine the model of Copernicus, which assumed circular orbits. If the eccentricity of a planetary orbit is 0, then Kepler's laws state 1. The planetary orbit is a circle with the Sun at the center. 2. The speed of the planet in the orbit is constant. 3. The square of the sidereal period is proportionate to the cube of the distance from the Sun. Actually, the eccentricities of the orbits of the 6 planets known to Copernicus and Kepler are quite small, so the rules above give excellent approximations of planetary motion, but Kepler's laws fit observations even better. Kepler's corrections to the Copernican model are not at all obvious. 1. The planetary orbit is not a circle, but an ellipse. 2. The Sun is not at the center, but at a focal point. 3. Neither the linear speed nor the angular speed of the planet in the orbit is constant, but the area speed is constant. 4. The square of the sidereal period is proportionate to the cube of the mean between the maximum and minimum distances from the Sun. The non-zero eccentricity of the orbit of the Earth makes the time from the March equinox to the September equinox, around 186 days, unequal to the time from the September equinox to the March equinox, around 179 days. A diameter would cut the orbit into equal parts, but the plane through the Sun parallel to the equator of the Earth cuts the orbit into two parts with areas in a 186 to 179 ratio, so the eccentricity of the orbit of the Earth is approximately, which is close to the correct value, 0.016710219. See Earth's orbit. The calculation is correct when the perihelion, the date that the Earth is closest to the Sun, is on a solstice. The current perihelion, near January 4th, is fairly close to the solstice on December 21st, or 22. Planetary acceleration. A sudden sunward velocity change is applied to a planet. Then the areas of the triangles defined by the path of the planet for fixed time intervals will be equal. Click on image for a detailed description. Isaac Newton computed in his Philosophiae Naturalis Principia Mathematica the acceleration of a planet moving according to Kepler's first and second law. 1. The direction of the acceleration is towards the Sun. 2. The magnitude of the acceleration is in inverse proportion to the square of the distance from the Sun. This suggests that the Sun may be the physical cause of the acceleration of planets. Newton defined a force on a planet to be the product of its mass and the acceleration. See Newton's laws of motion. So, 1. Every planet is attracted towards the Sun. 2. The force on a planet is in direct proportion to the mass of the planet and in inverse proportion to the square of the distance from the Sun. Here the Sun plays an unsymmetrical part, which is unjustified. So he assumed Newton's law of universal gravitation. 1. All bodies in the solar system attract one another. 2. The force between two bodies is in direct proportion to the product of their masses, and in inverse proportion to the square of the distance between them. As the planets have small masses compared to that of the Sun, the orbits conform to Kepler's laws approximately. Newton's model improves upon Kepler's model and fits actual observations more accurately. See two-body problem. A deviation in the motion of a planet from Kepler's laws due to the gravity of other planets is called a perturbation. Below comes the detailed calculation of the acceleration of a planet moving according to Kepler's first and second laws. Acceleration vector. See also polar coordinate, vector calculus, and mechanics of planar particle motion. From the heliocentric point of view, consider the vector to the planet, whereas the distance to the planet and the direction is a unit vector. When the planet moves, the direction vector changes. Whereas the unit vector orthogonal to and pointing in the direction of rotation and is the polar angle, and where dot on top of the variable signifies differentiation with respect to time. So differentiating the position vector twice to obtain the velocity and the acceleration vectors. So, where the radial acceleration is, and the transversal acceleration is, the inverse square law, Kepler's laws say that, is constant. The transversal acceleration is 0. So the acceleration of a planet obeying Kepler's laws is directed towards the Sun. The radial acceleration is. Kepler's first law states that the orbit is described by the equation differentiating with respect to time. Or, differentiating once more, the radial acceleration satisfies. Substituting the equation of the ellipse gives. The relation gives the simple final result. This means that the acceleration vector of any planet obeying Kepler's first and second law satisfies the inverse square law, where is a constant and is the unit vector pointing from the Sun towards the planet and is the distance between the planet and the Sun. According to Kepler's third law, has the same value for all the planets. So the inverse square law for planetary accelerations applies throughout the entire solar system. The inverse square law is a differential equation. The solutions to this differential equation include the Keplerian motions, as shown, but they also include motions where the orbit is a hyperbola or parabola, or a straight line. See Kepler orbit. Newton's law of gravitation. By Newton's second law, the gravitational force that acts on the planet is, whereas the mass of the planet, and has the same value for all planets in the solar system. According to Newton's third law, the Sun is attracted to the planet by a force of the same magnitude. Since the force is proportional to the mass of the planet, under the symmetric consideration, it should also be proportional to the mass of the Sun. So, where is the gravitational constant? The acceleration of solar system body number I is, according to Newton's laws. Whereas the mass of body J is the distance between body I and body J, is the unit vector from body I towards body J, and the vector summation is over all bodies in the world besides I itself. In the special case where there are only two bodies in the world, Earth and Sun, the acceleration becomes, which is the acceleration of the Kepler motion. So this Earth moves around the Sun according to Kepler's laws. If the two bodies in the world are Moon and Earth, the acceleration of the Moon becomes. So in this approximation the Moon moves around the Earth according to Kepler's laws. In the three-body case the accelerations are. These accelerations are not those of Kepler orbits, and the three-body problem is complicated. But Keplerian approximation is basis for perturbation calculations. See lunar theory. Position as a function of time. Kepler used his two first laws to compute the position of a planet as a function of time. His method involves the solution of a transcendental equation called Kepler's equation. The procedure for calculating the heliocentric polar coordinates r of a planet as a function of the time t since perihelion is the following four steps. 1. Compute the mean anomaly, where n is the mean motion, where p is the period. 2. Compute the eccentric anomaly by solving Kepler's equation. 3. Compute the true anomaly by the equation. 4. Compute the heliocentric distance r from the first law. The important special case of circular orbit equals 0 gives equals E equals m because the uniform circular motion was considered to be normal. A deviation from this motion was considered an anomaly. The proof of this procedure is shown below. Mean anomaly, m. Figure 5. Geometric construction for Kepler's calculation of the Sun, located at the focus, is labeled S, and the planet P. The auxiliary circle is an aid to calculation. Line XD is perpendicular to the base, and through the planet P the shaded sectors are arranged to have equal areas by positioning of point Y. The Keplerian problem assumes an elliptical orbit, and the 4 points S the Sun, at one focus of ellipse, Z the perihelion, C the center of the ellipse, P the planet, and distance between center and perihelion, the semi-major axis, the eccentricity, the semi-minor axis, the distance between Sun and planet, the direction to the planet, as seen from the Sun, the true anomaly. The problem is to compute the polar coordinates, r, of the planet from the time since perihelion, t. It is solved in steps. Kepler considered the circle with the major axis as a diameter, and the projection of the planet to the auxiliary circle. The point on the circle such that the sector areas vertical bar ZCY vertical bar and vertical bar ZSX vertical bar are equal. The mean anomaly. The sector areas are related by the circular sector area. The area swept since perihelion is by Kepler's second law proportional to time since perihelion. So the mean anomaly, m, is proportional to time since perihelion, t, where n is the mean motion. Eccentric anomaly, e. When the mean anomaly m is computed, the goal is to compute the true anomaly. The function equals f, m, is, however, not elementary. Kepler's solution is to use x as seen from the center, the eccentric anomaly. as an intermediate variable, and first compute E as a function of M by solving Kepler's equation below, and then compute the true anomaly from the eccentric anomaly. Here are the details. Division by a 2/2 gives Kepler's equation. This equation gives M as a function of E. Determining E for a given M is the inverse problem. Iterative numerical algorithms are commonly used. Having computed the eccentric anomaly E, the next step is to calculate the true anomaly.